Okay, students, let's understand the phases of compiler. Okay, as you know, compiler is a program that converts source program into a target program. Okay, so let us write this, the phases of compiler. The first phase of compiler is lexical analysis. Okay, so what is lexical analysis? See, let's understand this with the help of an example. This is the example: position equal to initial plus rate into 60. Okay, rate into 60. Now, what is position, initial, rate plus 60? These are the different tokens in this lexical analysis phase. Lexical analysis basically generates a stream of tokens. See, position is one token, initial is one token, rate is one token, 60 is one token, equal to is one token, plus is star is one token. What is a token actually? Actually is a particular category to which you can assign a group of characters to. For example, this position, the sequence of characters to position, they form into one syntactic one lexical category that is called token, because it is an identifier. It is an identifier. Position is an identifier. Similarly, initial is also an identifier. Rate is also an identifier. 60 is a constant. Equal to is an assignment operator. Plus is arithmetic operator. Star is a multiplication operator. So this fit into the operator category, and these fit into the identifier categories. So these are different categories of tokens. Okay, you can write simply ID1 and this equal to, then ID2, then plus, then ID3, then star, and 60, which is a constant. Okay, so these are how many tokens? One identifier equal to identifier 2, which is initial, identifier 3, which is rate, and then constant 60, star, plus, and equal to. Equal to plus, these are the operators. We can assign the category operator 1, operator 2, and operator 3. Okay, these are the different operators. Okay, these are different operators. So this is the output of the lexical analysis phase. This stream of tokens. And tokens fit into different categories: identifier, operator, okay, and constants. So this is the lexical analysis. Okay, and then we have syntax analysis. What is syntax analysis? Syntax analysis means to this stream of tokens we assign a hierarchical structure. What is that hierarchical structure? For example, this is fit into a grammar which is called identifier equals to expression. Okay, we can write this as identifier equals to expression. Position is an identifier. Okay, so we can write a grammar for this. Let's understand the syntax analysis phase now. Now, in the syntax analysis phase, the grammar that comes out to be is the identifier equal to identifier 1, then equal to plus this identifier 2, that is initial, then star, identifier 3, which is rate, and then 60, which is a constant. So this is the hierarchical structure that we put onto that previous statement. Identifier equals to expression means position equals to initial plus rate into 60. These are the identifier. This is a constant, and these are the operators. Okay, the internal nodes are the operators equal to at the root. For example, the first operation that is carried out is rate into 60. The rate is an identifier, is a constant. Rate into 60 is the first operation that is carried out. Then we carry out plus identifier plus read into 60. Then the next operation, which is at the root, is the assignment operation. Identifier equals to expression, this expression which is the result of this plus operation which is accumulated at this node, and then we apply the expression. So this is the output of the syntax analysis phase. Okay, now we come to the next phase, that is semantic analysis. See, I show the result of the semantic analysis here itself. What this semantic analysis does, semantic analysis is an optional phase. Maybe there may be requirement of semantic analysis or not. For example, if we consider these three identifiers as real, then we can convert this 60, which is a integer constant, to a real constant by applying an implicit operator, type conversion operator. Implicit type conversion, we can convert it into the real constant. Okay, by applying the one node that is int to real 60. Okay, so this is the semantic analysis. Okay, and then after the semantic analysis phase, we have intermediate code generation phase. What is this intermediate code generation? Now, this hierarchical structure that you obtained in the previous phase, that is semantic analysis, then we will write a intermediate code in the form of a 3-address code. 3-address code is a code in which we use at most 3 references. Okay, we use at most 3 references. So now again consider the statement position equals to initial plus rate into 60, and let us write the intermediate code, which is a 3-address code for this expression. What is the 3-address code? 3-address code is simply this. We take variable temp1 equals to position, and temp2 equals to initial, or we can say temp2 equals to rate into 60. Okay, and then temp3 equals to initial plus temp2, and then we write temp1 equals to temp2 plus temp3. Okay, so this is the intermediate code. See, or you can check with this is the 3-address code written for this expression. Original expression initial plus rate into 60 assigned to the variable position. Then this is a statement. So now to this statement we apply the 3-address code. Temp1 equals to position, temp2 equals to rate into 60, temp3 equals to initial plus temp2, and temp1 equals to temp2 plus temp3. Okay, so this is the intermediate code for generation. 3-address code, you can see here at most 3 references are being used. So it is an intermediate code, and it is independent of any programming language. Intermediate code generation does not depend on any programming language. It means it is not a machine dependent phase, it is machine independent. Okay, now the next phase is code optimization. What is code optimization? Code optimization is a phase in which we optimize the code. What is the meaning of optimization? We are improving the code for space efficiency and time efficiency. improving the space efficiency or the time efficiency. Space efficiency could be improved by reducing the number of variables, and time efficiency could be reduced by reducing the number of instructions. As we earlier did the intermediate code generation, now let us do the optimization of that, and it is also optional for maybe there may be requirement of optimization or not. Sometimes the optimization is not required because it will not significantly improve the execution time or the space efficiency, but sometimes intermediate code is required because it can change significantly the machine efficiency and its execution time. And what could be the case when it could generate the space efficient and the time efficient code optimization solutions. And this is actually because of the reason that sometimes the instructions are not much enough. So even if you improve the code, it will not significantly affect the execution time of the space efficiency. So it will lead to it will lead to it will lead to a code which is not required. Actually code optimization is not will not be required in that case, because if optimization is not required in this case, because you will have to spend so much resources on that optimization which will not be rewarded to you in return. Okay, so let us do optimization of this previous code. What is the optimization? Optimization of the previous code is see, first was the identifier equals to expression. So we write we can in this case we can use one temporary variable temp1. We can directly write temp1 temp2 equals to rate into 60. We can write temp1 equals to initial plus temp2. Okay, so this is the so now you can see that this is a optimized code, and here you are seeing that we have reduced one variable and there is no requirement of a temporary variable 3, so we can eliminate that, and our work is done with the two variables only, temp1 and temp2, and secondly some instructions have also been reduced. See, we are not requirement of temp1 equals to position, so that is not required, and secondly last variable that we are using temp3, we are not required that instruction also, and it means first we write temp2 equals to rate into 60, then we write initial, then we write temp2 equals to temp initial plus temp2. Okay, as you are seeing this in this way. So we do not require the next variable, that is temp3. We can write the code entirely with the help of these two variables only, and these two statements. So you can see the number of variables is reduced, and also the number of instructions have been reduced. So it is improving the space efficiency, and it is improving the time efficiency also. So this is actually when the code is very big. You have a very big code, very large coding files, where their optimization is actually worth, because that will significantly improve the execution time and the space efficiency of the code, and it will significantly improve our code in terms of space and the time. But if the code is not that enough, then we are not required for the code optimization techniques, because it will not it will increase the rather it will rather than improving the space and time efficiency, it will improve the computational overhead or the optimization overhead on the machine. Okay, so this is the code optimization phase. Now after code optimization, in the last phase, that is called code generation phase, which is a machine dependent phase. And in the machine dependent phase, code generation, we generate the code actually assembly language code. Okay, assembly language code. When we compile and translate them from a high level language to a assembly language, so Let us write the assembly language. Then let us take the reference for 8085 for generating the code generation. Now what is code generation? What is code generation? In the code generation, what we do, code generation, we generate the assembly code for the previous instruction. And what is the assembly code? Let us write the assembly code. We were writing temp2 equals to rate into 60 and temp1 equals to initial plus temp2. So let us write code generation for that. Let us take some registers and write MVI move immediate 60 to register R1. We will take the register first and then the constant move MVI R1 60. So move immediate R1 60. Then we write R1 is actually holding the constant 60 and we multiply with rate. Consider rate is present in register R2. Register R2, we move R in a rate into 60. We directly apply multiply. Then we apply multiply R2 to R1 and hold the resulting R1. Getting my point? R2 contains the identifier rate. So when you multiply R1 R2 and store the result in R1, you get the value of rate into 16 R1. Then from the next instruction we use add R2 contains add R3 and R1. Okay. Now result rate into 60 is present in R1. So we apply R3 plus R1 and store the result in R1. R3 we assume that contains, what does it contain? R3 we assume that contains the identifier initial. So the result of initial plus rate into 60 R1 is already contained the multiplication and R3 containing the identifier initial. So initial plus rate into 60 we are able to get in register R1. So this is the instruction set. This is the assembly language instruction set for generating the code generation. So this is the output of the last phase, that is code generation. Thank you.